Now the question is, though, how do we make use of this? We want to be able to take advantage of the fact that we have electron transfer going on, and we want to be able to extract electrical energy from that electron transfer. So what engineers and scientists have come up with is this ingenious way of separating the two half reactions. Okay, here's an example of the same reaction that we just looked at, only the reactants have been separated physically, literally in space, into two separate beakers. And in this way, you're going to force the electrons, instead of going straight from, for example, the zinc to the copper directly, because they're touching, they come in physical contact with each other. The copper ions, of course, are moving around all the time. Whenever they bounce into the zinc, the electrons will be transferred, the product is made. In this case, we physically separate the zinc from the copper ion and force the electrons to travel through an external wire. And when electrons move through a wire in one direction, you get a direct current, and it's a form of electricity. Okay, and so this whole field, electrochemistry, is the study of the interchange of chemical and electrical energy. Okay, so we have the basic concept, the fact that electron transfer does occur, and now we've got this whole new discipline studying how can we better understand, better make, better do, better take advantage of this electron transfer to make devices that are useful in producing electrical energy. So in this picture, this is the zinc. This is just a solid piece of zinc. This is a solid piece of copper. And over here, the blue solution here is there's copper ions floating around and sulfate anions floating around. And what happens is the zinc, when it gives up electrons to the copper, it forms zinc ions, and they just go into solution. Well, there's probably some sulfate over here too. And then anytime you have a circuit, you have to have a circular movement of charge. And that's why there's one little thing that's needed in order to make these electrons move from one reactant across a wire to the other reactant, and that is this thing here called a salt bridge. We'll talk more about that. Okay, but it's a way to complete the circuit. Alrighty, and so what happens is the zinc, a little bit at the very beginning, before you connect the wire, a little bit of the zinc, tiny little bit, will dissolve into solution, and you'll start building up just a little bit of what we call potential. Electrons that want to move, they want to move off the zinc, so the zinc can go into solution, and we build up a little potential. And this is sort of what we call the push. These electrons want to be pushed off the zinc. And at the same time, when you have the copper and the copper 2 in solution, at the very instant before you connect these, the copper 2, a little bit of it is going to pull some electrons out of this metal, because it's a sea of electrons, and a little bit of copper is going to plate out onto the copper from the copper solution, and that's going to give us a little pull on this situation. We want to pull some electrons into this solution, and we want to push some electrons off of this, and it's a push-pull kind of situation. As soon as you connect the wires and connect the salt bridge, you have a potential set such that the electrons will fall essentially from the metal that's going to be oxidized to the metal that's going to be reduced, metal ion that's going to be reduced. And so this is how we generate an electric circuit, by separating two half reactions. Okay, and I want to show you, let me see. So what's going on here then is the zinc is giving its electrons to the copper ion. It's just that they're physically separated, so the electrons have to pass through the external wire, through the piece of metal, down into the solution where they're picked up by the copper ion, and then the copper just, what we call, plates out onto that piece of metal there. All right, so this is your basic, this is called an electrochemical cell.